Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to introduce Professor Stephen Kortler from Harvard University. Shlomo got his PhD at Princeton University back in 1994 or so, 1995. He's done lots of work, many areas, mesh parameterization, image-based rendering, and today he's going to be talking about parameterization, I think.
Thank you. All right. So I'm going to try to go really quickly through the preliminaries, since this is a crowd that should know them. We've got a mesh. It's got vertices, edges, and faces, so it's topologically a disk. It has a boundary, and we want to flatten it into a 2D domain. We could give it UV coordinates, and the boundary might go to that outer circle. There are lots of things one might be interested in, such as minimal distortion. So you could look at a little piece, and look at a neighborhood, and there it is in 3D, and take a look how what its shape is in 2D. And this is all interesting and nice, but that's beyond what we're going to talk about. We're going to talk about the simple question of, when we flatten this, is this going to be an embedding? In particular, one thing you can say is, are any edges are going to cross? So here's an example of a non-embedding. So you saw that the green one went up and crossed over. I'll show that again. Blue, green went up, then down. So that's a bad. We don't want this to happen. If this happens, if this doesn't happen, then the mapping is 1-to-1. We can do texture mapping. We can draw this nicely. If this happens, all hell broke loose. We're not happy. So we're going to talk just about this one question. And there are all kinds of applications, texture mapping, remeshing, et cetera, et cetera. So here's texture mapping. Here's remeshing. You sample. You flatten, you sample. You build a Voronoi, and you put it back up on the surface. There are all kinds of applications. Again, I'm going to skip these for this audience, get to the point. How are we going to do this? So Tut looked at this problem. He actually wasn't doing graphics. He was doing graph drawings of graphs. But it's actually the same problem. So he's got a graph. It's planar. And he's going to take the boundary, which I'll show in blue on the top, and map it to some convex polygon shown in the bottom. Then he's going to take a spring and attach it along, think of attaching a spring along each interior edge. And the spring could have any strength, and there's lots of discussion about what are nice strengths, but we don't care about that. And then we're going to move the vertices around. So here are the springs over there. And then we're going to move the vertices around until they minimize their spring energy. So they wiggle around until they get here. Then we're going to draw, this is actually very easy to solve. It's a single linear system. And then we're going to draw straight lines connecting the positions of each of the vertices based on their edges. So I'll show you a quick demo that I shamelessly stole off of a Microsoft page. OK, so here is what happens when you, actually that was the wrong demo. Let's go to planarity maybe. Here we go. There it goes. So we put springs. These guys were locked down. These guys moved around. We draw straight lines. That's the demo for now. And the theorem says that this will work. This will be embedding. Lines won't cross. Okay, that's the theorem. There's actually a proof, but it was quite complicated. And since then, there have been many, I'll call them somewhat simpler proofs. But they're actually not that simple. And the goal today is to come up with a nice, clean way of thinking about these things. So we're going to describe some simple results about something called oneforms. This will give us a very simple proof of the very useful Tut algorithm. And then we'll talk about generalizing it to non-convex boundary and higher genus once we have all these tools. Okay, that's going to be our goal. So we need to define one animal, which we're going to call a oneform on a mesh. Very simply, we're going to take, here's an edge, and we're going to put a number on that edge. And this is actually in this direction. And in this direction, we'll put the opposite number, negative 3.1. Let's say these are real numbers. So obviously, another way of drawing this, which might be easier, is to just draw one arrow in the positive direction. And the negative number in the negative direction will be implied. All right? So a oneform, you will think of that as a drawing, an association of a number to each edge with a direction. That is going to be a oneform. There's no zeros also. It's always going to be positive numbers. Now we need to define what's called an index of a form at a vertex. So we have the edge, we have the faces, so we can order the edges around the vertex. And we can look at the directions of the arrows. So in this case, all the arrows went out of a vertex as you went around. So the number of sign changes is 0. So 2 minus 0 over 2 is 1. So this is a source, and we're going to call it index 1. If we had all the arrows coming in, that would be a sink. It would also have index 1. Okay? Let's look over here. Here we have out, 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 in, 1 sign change, in, out, 2 sign changes. Exercise, this always has to be even. Think about it. So now we have 2 minus 2 over 2, index is 0. And we're going to call this the non-singular case. And over here we have out, 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 in, out, no, in, out, 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 4. 2 minus 4 over negative 2. So our index is negative 1. It's important to realize it's less than 0. And we're going to call this a saddle. Whenever there's more than 2 sign changes, even number, so 4 or 6, etc., the index will always be negative from this equation. Is everything clear what we're doing here? Yeah. We can play the exact same game with faces. So here we walk around the face. Again, we have all the ordering information from our mesh. It's all going in one direction. We call that a vortex. There are no sign changes. 2 over 2 is 1. The index of a vortex is 1. Call it a swirl as well if you want. Here we have going out, going to the right, to the right, to the right, switch. Switch, 2 switches. 2 minus 2 is 0 over 2, index 0. We're going to call this non-singular. Non-singular, as we're going to see, is actually the desired case. It's going to be the average case, the usual case. We'll see what that means in a second. And here we've got out, switch, 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 no switch, switch. It has 4 switches. 2 minus 4 over 2 is negative 1. So it has a negative index. And we're going to call this a saddle. Okay? So again, we have our mesh. Oneforms are numbers with arrows. We can look at the pattern of arrows, and we can assign an index at every vertex and every face. Michael?
Do the red circles have meaning here in practice?
Yeah, that was helping me count, actually. The red circles when we didn't have a change as we went around here. This one didn't have that. This was the red vertex here. Okay. So now we can state a very simple theorem. If G is a closed-oriented mesh, so it's a nice mesh, it has no boundary, and we look at all the vertices and add up their indices, and all the faces that add up their indices, we've got to get 2 minus 2G, where G is the genus of the mesh. So a sphere would be 0, a torus G would be 0 for a sphere, 1 for a torus, etc., etc., etc. A simple case of this was proven by Banshoff. We proved it as well, but a slightly earlier version appears in a survey by Lovash. It's a very simple theorem, in fact. You just count up corners, and you need to apply Euler's formula. And other than that, it comes out really straightforward. Okay? So we'll call this, this will be our theorem in green. This will be the green theorem, because we use green letters. This actually might look a lot. In fact, it's very related to what's called the Poincare-Hopf index theorem, which talks about the number of singularities if you have a smooth vector field on a surface. People might call it the hairy tennis ball theorem, or the hairy scalp theorem, etc. And so this is just sort of a point of reference. It's actually essentially the same theorem in disguise, but it's dealing with meshes. Okay. So we have this idea. We have oneforms. We have a theorem, index theorem. Let's take a drawing that came from a Tutte algorithm. So we're just looking at a little piece of that drawing. It might have crossings. We don't know about that yet. That's actually what we're trying to prove doesn't happen. So we're going to possibly have drawings. We're not crossings. We're not going to assume that. So what are we going to do? We're going to take any direction. So here's a direction, dotted line. We'll call that direction Z. We'll take all of our vertices, and we'll project them onto that Z axis. We're going to look at the difference in the Z axis, and then we're going to record that in a one form on the mesh. So for example, here, this point was, let's say, this point here, the blue point was 3 above here, some amount above here in this direction, so that became a 9 along that one. So the green is above, let's see, green, blue is above green, so the arrow goes that way. Red is below green. The arrow goes that way. Okay, so we've just recorded these differences along all the edges in the graph. Okay, and we're going to assume there's no zeros. We'll talk about zeros very, 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 very quickly later on.
Zeros would happen if two points lined up and project onto the same point.
Yeah, so like in this case, if this direction was a little bit different, if it was actually perpendicular to this line, they'd both hit the same point, then we'd get a 0. If they're connected by an edge, we'd be getting a 0 there.
Yeah.
So we'll have to deal with that later because that just annoys us. Okay, as zeros often do. Okay, so we have a drawing, we pick a direction, we get a one form. So what do we know about this one form? Well, let's look at a face. So we'll pick the z-axis. We know when you walk from here to here, here to here, here to here, you got to get back to where you started. So therefore, if you walk along the directions, it can't always be going always downhill or always uphill. So it can't be a vortex. Right? That would mean you're going around in a loop, always going downhill, and somehow still get home. Although there was a friend of mine who had I remember having him. He was a roommate. And he's on the phone. And he's like, "No, you can't just bike downhill all the way from a loop and still get home." So they weren't aware of this theorem. All right. So what does this mean now? This means it can't be a vortex. So in this one form, this face has to have a non-positive index. It could be a 0 or a 1 or a 2 or a 3, but it can't be, a 0, a -1, a -2, a -3, but it can't be a 1, because a 1 is a vortex and there can't be a vortex. Let's look at a vertex. So you know a vertex, it was relaxed using these springs. So it's got to be inside the convex hull of its neighbors. It can't be out here. The springs would pull it down. It's kind of self-evident, sort of easy to argue. Michael's squinting, so I'll say it again. I'll make it better, right? This vertex, it can't be outside, let's say, the triangle of these three vertices. If this vertex were out here, it's got springs going here, here, and here. Those springs would pull it down. All right? So what does that mean? If we look at these numbers, some guys have to be above it in this direction or any direction, and some guys have to be below it. Right? Which means that in the one form, this vertex, by virtue of the fact that it's relaxed in the springs, cannot be a source or a sink. So again, it must have non-positive index. Sources and sinks have index 1. Everybody else has index 0, -1, -2, -3. Okay? So faces have to have non-positive, and these interior vertices have to have non-positive.
In fact, if they add up to 0, is that accidental? I mean, 5 and 2 is 7.
That is, I'll call that accidental, yes. They should add up to 0 with respect to some weights, actually the weights of the springs. So if all these were actually unit length edges, then they would add up to 0, because they would actually be at the center of mass.
Yeah.
So it's actually not, it's not completely accidental. So good point. Not important, but not accidental. Boundary. The boundary is a little bit more complicated. I'm just going to draw one little picture. I told you the boundary is a convex polygon. All right, so let's draw a convex polygon, pick a direction. Let's just pick north. There's always going to be a guy on top and a guy on the bottom, unless something's flat. We'll deal with that later. Okay? So the upper guy, he might be a source. He might be above everybody with respect to the up direction. And the lower guy, he might be a sink. He might be below everybody. In fact, he probably should be. But anybody else, these guys on the side, right, they've got to have somebody above them and somebody below them with respect to the direction that we've chosen. Okay? So all the vertices, except for possibly 2, are not sources and not sinks. And so once again, they must have non-positive index. Okay? So now we've done all the accounting, and all I have to do is add it all up. All faces have non-positive index. This is due to the fact that you can't bike downhill all the way and go home. So it's got to be 0 or negative. All vertices have non-positive index except for maybe 2. Let's just call it except for 2. So we have 0 or negative for all the interior and all of the sides. And then we've got 1 on top and 1 on the bottom. These guys are 0 or negative. 1 and 1. There's our 2. Now we have this graph we know is a planar graph, which means that if you include the outer face, we have a sphere. A sphere has genus 0, which means that when we plug in 2 minus 2 times 0, we get 2. Which means, and we have our index theorem, our green theorem, which is that the sum of all these things have to be 2. Okay? So what does that mean? Well, what it means is we can't have any negatives here. Because if you had a negative here and you have to get to 2, you'd have to have some more positive to cancel it out. But there's nowhere to get that positive. All right? So therefore, there can't be negative. Which means that in the one form, there can be no negative indices if this came from any projection of a drawing that came from a spring system. Okay? So we're going to call this the red lemma. Okay? Is this clear? Use? Yeah. All right, now we're pretty much in the home stretch at this point. Let's look at let's look at what we're trying to avoid. Here's a typical case of what we're trying to avoid. Here's a neighborhood, and topologically it's black, 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 purple, green, yellow, blue. That's the topological ordering of our mesh. Okay? But something bad, let's suppose something bad happened, that geometrically, when we drew it using the algorithm, this happened. Suppose this happened. All right? And I'm going to call this not a wheel vertex, because it doesn't look like a wheel to me. And in fact, what happens? Well, let's pick the y direction as our z direction and look at above versus below. So here I've laid them out in topological order. Blue was above, yellow was below, green was above, and then blue was below. So if I look around, I've got 1, 2, 3, 4 sign changes, which means I've got a saddle here. Okay? So if you run the Tut algorithm and this appears, that means in the projection you would have had a saddle. But we just went at great length to prove that there couldn't be saddles. So that's a contradiction. Okay? So this can't ever happen when we solve with the spring system. And here's some more pictures. Okay? This can't happen. This also can't happen, where you kind of go around twice before you loop up. Okay? I got no problems with this guy. This could happen. We'll call this a wheel. You could define it, but you sort of already kind of know what it is. Here's a face. It's not convex. That actually means if we pick a direction, we'll find we could pick a direction for which we would find a saddle. That couldn't happen. This goes around twice before coming around. Any direction, we'll find a saddle there. So that can't happen either. Okay? This is convex face. Again, I could define it, but you kind of know it when you see it. This could happen. All right? So in fact, we can summarize this by saying what we've now shown is that in the result of a Tut drawing, every face must be convex. Every vertex neighborhood must be a wheel. And I'm going to say, I'm going to give it a word. I'm going to say locally this is an embedding. It means.
But you had a particular way of assigning the weights, so you haven't proved that this is true in general for any assignment of.
Well, there was nowhere in the discussion where I used any particular weights. This is actually
assigned it by projecting onto this line.
Oh, this is for any line. So this whole theorem here says.
Right, but it has to be projection onto a line. Couldn't you assign weights with some other algorithm?
Okay. So the weights are used to solve for the positions of these vertices in space. Okay? So those are the spring weights. And our discussion here now is true for any spring weights, because I didn't say anything about them. So no matter what spring weights were, no matter what the spring rates were, my discussion applies to them. Now there's a projection operation.
Right.
That projection operation creates a one form out of the drawing.
Right.
And what we've shown here is that if I have a drawing that came from Tut, if I pick any, I didn't tell you to pick this one. If I pick any one of them, that would give me a one form. There could never be a saddle in that one form.
Right. But you haven't shown that an arbitrary one form satisfies this, because you've only proven that a one form that comes by this projection onto a single direction satisfies this.
Right. But what I've shown now is I'm just telling you that this drawing could never occur from a result of Tut. Because if this was the drawing, I would say, well, I'm allowed to pick any direction I want, and there should never be a saddle there. So let me pick this direction. I see a saddle there. That can't have happened. Okay? I think I'm unfortunately missing something.
It's my problem, not yours. I think I understand.
Your problem is my problem, especially in an audience of 6 or 7. Okay. So what I'm arguing here is the way it is the springs with the weights give me a drawing Then I get to pick any direction, and I'm arguing what happens in that when I do that. And I've shown that no matter what happens, I should never be able to detect a saddle there. Yet, in this drawing, if I choose this direction, I will detect a saddle. That contradicts what we said could happen.
Okay.
Michael.
So since there's only 7 of us and I did come in 5 minutes late, I assume I missed one thing, which was that you set this all up by assigning positive spring weights to this thing and let it relax.
This is correct.
That's
the only assumption.
Slide I missed. Probably.
And we lock the boundary to be a convex polygon, the outside.
Okay. Got it.
And there's no springs on the outside. Okay, so we're going to call this locally an embedding. When locally the neighborhood in the mesh maps nicely to the neighborhood in the plane. 1-to-1, there's no crossings. Now, here's a kind of obvious lemma. I'm not going to prove it. If every neighborhood is locally an embedding, and the boundary is simple, then we're going to globally have an embedding here. Okay? It kind of means that if nothing goes wrong anywhere, it doesn't go wrong. Now, we've already proven that every neighborhood maps nicely as an embedding during the flattening, during this parameterization. And our boundary is a convex polygon, so it can't intersect itself. And so we're done. Okay? So again, what we showed first we showed that every little neighborhood here has to look like a little neighborhood here. We already know that the outside goes to a loop here. And we're going to sort of put that together to say that, in fact, there can't be anywhere where you get more than one triangle mapping to the same position.
And the boundary, if the boundary weren't convex, then you'd have a problem that locally it wouldn't be.
We'll get to, yeah, we're going to deal exactly with non-convex boundaries in 3 seconds. Okay? Actually, so we're done. I get to put QED here. And we now can breathe deep, and we sort of believe now we have a proof of this algorithm that's 40 years old. There were other proofs, obviously, but this was kind of pretty easy. So makes this happen. So enjoy that. There's some details. I don't want to spend too much time on them. They're actually tricky, which kind of takes away from my claim that this is so simple. What happens if I pick this direction so that these guys go to the same spot? I drew them in a separate spot so you can see them. That means that on the green-blue edge here, we get a 0. And the whole discussion just collapses. Everything falls apart. No argument. The way we need to fix that is using a perturbation argument. And the argument is, here's my one form. It had some arrows, but it had some zeros. I always can find a nice perturbation. It's kind of got everything sort of nice patterns. And I can always add epsilon of it to this guy to get me something new. All right? Now there's details of what's a nice perturbation. The idea is if you can find one of these nice perturbations, then it doesn't anything that has a sign here doesn't lose that sign. And the new zeros get their signs all in some kind of consistent setting. And therefore, when you do this, all the previous arguments still can be made to work. Okay, so I'm not really giving you the details here. I'm kind of waving my hands. And the existence of one of these actually goes back to work by Lovash, Lineal, and Vidgerson, 88, using a rubber band kind of argument. That you can always find rubber band patterns with no zeros in them. There's one more detail, which is, can there be either, here's a 0 area face, or a 0 length edge, or 180 degree internal, can there be these degeneracies in the drawing itself? So before, it was a nice drawing, but I picked something hokey, and we've shown here that, well, you can at least argue, you can run through the whole argument and you won't get saddles. But now I want to say something stronger. I want to say that something like this can never even occur in the drawing. And the kind of argument I'm going to use, again, I'm not going to go through the details, is that if this did exist, I could go back to my previous slide and actually find a perturbation that would have turned this into a saddle. Okay, so I'm not giving you the details again, but this is so close to being a problem that, and perturbations are actually pretty easy to find, I could have kicked it into the illegal position. But since you couldn't, again, you get a contradiction, everything rolls down. This actually requires what's called 3 connectivity of the graph. What it means is that there's no way, if you disconnect 2 vertices and all their edges, the graph stays connected. If the graph is not 3 connected, that is, if I pull 2 guys away, if I pull 2 guys away and it falls apart, then these are actually quite typical. Okay? So the complete theorem needs 3 connectivity to avoid degeneracies in the drawing.
Strictly convex on the polygon.
Yes. Now everything's strictly. What's that?
The outer boundary has to be strictly convex.
That's actually, no, that doesn't have to be. It turns out that that's actually a subtlety that the stronger proofs actually do not require it. It can be actually not strictly convex. And you still, actually you might think, wait a minute, what's going to happen? You'll say, wait a minute, if this is a vertex and a vertex and a vertex, and they're not strictly convex because here's the rest, and what if there was an edge here? Then the spring would make that tight. And the answer is, remove this vertex, this edge falls off, so this wasn't three-connected. So yes, that would happen. But for example, if it was non-convex, but this guy had edges like this, that's three-connected and it's perfectly fine. Okay, so all is well in terms of our storyboard. Okay, that's a real deep breath because we've now completed everything we're going to say about the classical Tutte theorem. Tutte theorem says you run the algorithm, it works. We've finished arguing about that. Okay, now we're going to look at non-convex boundaries. I don't want to say too much about them, but the basic algorithm assumes that you take the outside and make it convex. And for a lot of reasons, that's not good. It'd be nicer to have a free boundary. And now I'm not actually going to give you a way of solving. Also, this is even nicer, multiple boundaries. Here we had these eyes in the mouth. So we want to be able to deal with that too. So I'm not going to tell you how to solve this problem. I'm just going to give you sort of we'll call it a checking result. It's sort of a main result. And here's what it states. It states if you did a drawing and you locked the outer boundary to be non-convex, and there was a problem somewhere, there was some crossing, you would be able to detect this at the boundary. Okay? So if I had a non-convex boundary and something went wrong, I could see it right by looking at the boundary. Right? Sort of the converse of that is if you could come up with a method that forces the boundary to behave properly, then you know that method is now going to be sound. Okay? I'm not going to propose such a method, but I'm just saying what this implies. So here's an example. What went wrong? Here's an example. This vertex, these are all sort of convex. This one here is a reflex, right? He's not like nice and convex. He's reflex. One could define that, but hopefully the picture is clear. What happened here? Well, he's got some neighbors. Here they are. Dun, 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 dun. This is some face. And he's not in the convex hull of his neighbors. And that's actually going to be the test. So first let me show you another quick example from the stolen demo. So I'm going to move a vertex here, like this. I'm going to resolve. And that worked just fine. So now I'm going to move it further. Now it's not convex anymore, but still fine. And now I'm going to move it really far. And it's not fine. But what we see here is this guy's got 3 neighbors, 1, 2, 3, and he is not in their convex hull. I'm going to actually prove that that's equivalent. That's essentially sufficient and necessary. That's really sort of characterizes failure. That's exactly what failure means. So here is the complete statement. Yes, use.
Back up to 2 sides. You have the multiple boundary case.
Yes.
So it's an internal boundary. Is it any special case? If you treat arbitrary number of sides for a face, can you just consider it to be a polygonal face?
Yes, you can. The real difference is going to be that I'm going to lock these down, let's say. It is a subtle point, but semantically I'm going to lock these down. And you could imagine there's a face there, but it's not important anymore because so I take the outside of the eye and I lock down where it's going to be. And then I run the rest of the algorithm. So there's no springs moving these guys. It's really the same thing as if there was a face and I locked down all the vertices around it. We just don't care about that face anymore. So in that sense, yes. It's yeah.
So with this free system here, like the mouth that we see there it's a non-convex face, so we would never see this in a relaxation system.
You would never see this right. If you didn't lock it down, exactly right. You wouldn't see this because we proved that can't happen. But here I said, boom, this is it. These are no springs on these edges. I just tell you where they are, or some new fancy algorithm that we don't know yet tells you where they go. So here's the statement. Basically, it says that, again, G is our mesh, and it's 3 connected. And the boundary, if you walk around, you get 2 pi. So it doesn't go around twice. You do something really, really annoying. And what else? We're going to look at the same thing. We have inner boundaries. They have to go the other way. And they also go around once. They don't go around more than once. Then, if we look at in our tut drawing, if every reflex vertex is in the convex hull of its neighbors, then for any projection, no vertex or interior face will be a saddle. Okay. So if this is true, and all this other kind of obvious stuff, then any projection will, in fact, not be a saddle. And the proof is just really more careful counting. Okay. So again, the argument then states that if we've checked the boundary and everything looks good, so each face will be convex, each vertex neighborhood has to be a wheel, locally we have to have an embedding. Now we have to add an addition. If the boundary is simple, I mean maybe the boundary crosses itself. That could happen. Then it's not going to be globally embedding. But if in addition the boundary doesn't cross itself, then again we could take the local embedding property and turn that into a global embedding property.
But it's nowhere near as nice as before, because now you have to do it and see, whereas before you knew it would work.
That's why I told you in advance, right? We'll call this a checking theorem. So, I mean, the question is, what can you do? And I don't have the answer. I mean, there are methods that take meshes and create linear systems, and you can check. And in fact, they're not always successful, and they don't claim to be. And so it's really an open question. Is there a method which is, in some say, nice, maybe it's linear, and always works, and has some other nice properties as well? If I give you a triangulated graph and it's already on the plane, and I run my algorithm, it shouldn't change it. That will characterize the question. And you're right. I haven't answered that question. I've just pointed out that all the action happens at these reflex vertices and checking whether they're in the convex hull of their neighbors. And that's really all that. That's the key. That's the Achilles heel of the problem.
But it's like, since you had to try it first and then check, you're saying I can make the check really simple, only look at the boundaries. But you had to compute the.
I'm not. I don't argue. I'm not. Yeah. Here's an example. Okay. I'm not telling you. I'm not saying this helps us yet. This is right. So I'm not going to defend it.
Okay.
If you wanted to do something, suppose you wanted to add some sort of nonlinear optimization, which sort of really told guys that certain things can't happen. Well, now what I'm arguing here is that the nonlinear optimization only has to happen at the boundary. So maybe this could somehow simplify your some nonlinear algorithm, which maybe helps. But I'm not. This is a checking. This is an after-the-fact condition. It's not. I'm not giving you anything constructive.
I think the Levy example there probably has negative edge weights in the interior, so.
Even with positive edge weights, it can happen. We have verified this, and they.
Right.
Yes.
But in the presence of negative edge weights, it's not sufficient to just check the boundary.
Everything we said assumes positive edge weights from the. That was the one assumption we made when we therefore assumed that spring things put you in the convex hull. If you have like repulsive things, anything could happen. And so there are some methods that have negative edge weights, and I'm not even saying anything about those methods. So correct, Levy happens to have negatives. But even if there are cases where the Levy still gives you all positives, but still gives you flips, is in fact the state of the arch. Okay, time for another deep breath, because we've now finished all of our disks. So for disks with a convex boundary, it's tut, and we sort of had oneforms to prove that. For the non-convex boundary, we stated some conditions that don't satisfy John one bit. And now we're going to move on to non-disks. Curmudgeon John. So here are non-disks, and I want to do something with them. And again, the answers were going to be partially satisfying, partially unsatisfying. So don't get your hopes up too much, John. I got to warn you. This is not going to solve all your problems. So what do people often do is they often cut. That's the most typical thing. You cut, and then you get some sort of boundary, and you move on. But that involved cutting first. And that's kind of artificial, and you just kind of made it up. So we want to leave that. We want to cut as little as possible. All right. So now we need to create some more words now, just because we need to add like 2 or 3 more words before we go on. So let's go back to our one form. Let's look at our face. We had our face where we knew that you couldn't have a vortex. And another way of stating that is that the delta z, that's what we're going to call the number on this half edge h, when you add them up, has to be 0. right? Under any coordinate system, my xz value has to get back to the beginning when I walk around a face. And we're going to give this property, if this happens, we're going to say the face is closed. And really the one form with respect to the blah, 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 right? It's closed. It's just a word. It means this, and we've already seen it. Here's one more word. Before we had that vertex, it was sort of balanced by the springs. Okay? And therefore, it couldn't be a source or a sink. And it was pointing out, actually what Jim Blinn pointed out, was that actually where it lives, the weighted sum of the edges, where the weights happen to be the spring weights, if you add those up, you have to get 0. And it's not just it's always not just inside the convex hull. Where it is, it actually, if you look at the springs and add, look at the amount that you're above or below, and weight those by the weights on the edges, you have to get 0 as well. So we didn't actually use this particularly, but we're now going to write down a specific equation. The weights of the sum of the edges each period must be 0, and we're going to call the vertex in this case co-closed. And this is with respect to some set of weights. So a one form is closed in a face if when you walk around it you get 0. And a vertex is co-closed if when you walk around it you get 0. But maybe you get to use w's when you add them up. But these w's could be anything as long as they're positive. We're just going to fix them. All right, now I've got a mesh. And suppose that and I put a one form on this mesh. And suppose that every face is closed. And every vertex is co-closed with respect to some fixed set of weights that I've chosen in advance. Then we say that this one form is harmonic. So we have a third word. Just means that we're both closed at every face and co-closed at every vertex. Right. What do we know about this? Well, actually, there's a nice theorem. It's by Mercott, 2001. That if once I fix my weights, blah, 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 the harmonic one forms form, I guess that's a poor verb there, a linear space of dimension 2g, where g is the genus. Okay? So I give you a mesh. It has a genus. Sphere would be genus 0. Torus would be genus 1, etc. I ask myself, how many harmonic one forms are there? The answer is it's a linear space. So if I can find 2 harmonic one forms, if I add them up, I get another one which is harmonic. Or if I take a harmonic one form and I multiply every number by 10, it's still harmonic. It's still harmonic. So it's a linear space. And in fact, how many elements we need as a basis is 2g. The argument's a little bit involved. It's not my argument anyway, so take it for granted.
I'm trying to see the relationship between the closed and co-closed and the non-singular early on in the talk, the 0 relationship.
Well, let's see. Yes. Things that are closed, faces that are closed, are either non-singular or saddles. They're not vortices. That's what we used before. Okay? A vertex that is co-closed is not a source or a sink. It's either non-singular or a saddle. Okay, so you're right. So co-closed means not a source or a sink. It implies not a source or a sink. And closed face implies not a vortex. Okay? The counting theorem is what we needed in order to get rid of the saddles. That was sort of a global theorem. These are local statements that state you are not positive index. Is that good? Okay. So now we know how many harmonic one forms there are I can put on a mesh. All right, what does this help? Let's look at genus 0. No null space. There's nothing you can do. There are no non-trivial. Non-trivial just means put 0 on every single edge, right? There's no non-trivial harmonic one forms. So I'm not going to say very much here. All we can do is what we already did, which is remove one face, and then now you have a disk, and run tut. Okay, so I don't want to say anything more about this. Genus 0 is essentially not much you can, we already talked about it. We actually did do cutting. Okay, what are you going to do? All right. So that's genus 0. So let's look at higher genus. So the nicest case, as often the case, is genus 1. But let's look at an algorithm first. So here's an algorithm. It goes back, it's really gooey out, I would say, give this algorithm to. Pick 2 harmonic, we said there's a null space. So there's a big box full of them, they're linear, it's got some dimensionality. So pick 2 of them. And let's assume they're linearly independent. So here's one of them, it's got some numbers on it, and here's another one, it's got some numbers on it. All right? Now pick a random vertex to start with. Let's say the blue. Let's say that kind of cyan guy. And we're going to map him to the origin. Now, I'm going to look at an edge and say, OK, let's go up in y by 1 and over in x by 5. So I go here, and I draw a straight line. So this process is called integration of the one-forms. Now I went from green to blue. Well, I went -2. That takes me down to 3 in y. And -2 here. That takes me from 1 to -1. Okay. You might ask, what happens if I had just gone from blue to black this way? Well, in fact, I would have gotten -1 and +3, which is where I already am. But that has to be because of the closed property. Okay, so the closed property tells us that no matter how I go around a face, I'll get back to the same place. So it's, even though I did some arbitrary things, I chose this guy first and I went here, that didn't do anything funny. It's all kind of didn't make a difference. Okay, so it's kind of, once I've chosen these guys, this drawing comes out quite naturally. There's no funny business going on. And I keep doing this. And I keep on drawing more and more vertices by integrating along these two one-forms. So maybe it looks like this. Now, by the way, this is kind of the inverse of what we saw before, right? Before we took directions and we took projections, and that gave us one-forms. Now we're taking a pair of one-forms and integrating them to reconstruct a drawing. Right? So this is kind of a little bit of an inverse of what we saw when we were talking about the disk case. So now we're going the other way. Okay. So what happens if we have a torus? So this is our torus, genus is 1, and we keep on laying out faces, lay. And eventually, we're at some vertex. Eventually, we come around, and maybe we're at the same vertex, but we've kind of gone all the way around the loop. So we want to keep going. So if we keep going and integrate, we might get, imagine getting another copy going that way. And if we keep going, we might get another copy, and another copy, and another copy. So I just keep on integrating, keep on walking x, y, z's along edges. And one might imagine that if I went around, I'd be somewhere else. So if I keep going, I might get a whole other copy going on. All right? And so here I drew, 5 copies as I went around various ways. Now you'd say, well, I started off, I got this boundary. Maybe it was important where I started or something. But that's not true. I could have started anywhere. I could have started somewhere else, and maybe this was the first version of the mesh that I sort of visited. And then if I went some more, maybe I would have seen this. Okay? So even though I did make some choices, they were all completely irrelevant. So again, this is very natural. The question is, I drew a very nice picture where there were no crossings. Right? And everything looks like it's a nice drawing from the infinitely unwrapped torus to the plane. And the question is this in fact the case? Now here's one more copy. And here's another. All right. So, in fact, yes, for genus 1, we're going to say a theorem which states that, in fact, the embedding globally is always valid. This theorem also does appear in the same survey by Lovash. Again, different proof completely. We're going to prove this completely in one page using all the things we've already talked about. So here's the proof. All faces are closed by definition because it's harmonic. So the index is less than 0 in both one-forms. All vertices are co-closed. So their indices are less than 0 in both one-forms. This is actually easier than the disk case, right? Because there's everything. There's no exceptions. Everybody is less than 0. The green theorem, the index theorem, G is 1. 2 minus 2 is 0. So the indices, since they can't be positive and have to add up to 0, can't be negative either. Otherwise, you'd be in the red. So therefore, they all have to be 0. Hence, no saddles in either one form. Because saddles are negative indices, and our index theorem and our inequalities have sort of locked us in. Hence, in the drawing, all vertices must be wheels and all faces must be convex. Because if they weren't, then you certainly could find a saddle in your drawing somewhere. Yes. So QED, we're done. Global embedding. We need a little bit more sort of kind of flowery word to get from the local to the global, and I'll skip that. Okay? That's the torus. Torus case works. Okay, on to higher genus. And again, we're going to get sort of into a John Snyder situation here where we don't have a complete answer. We'll just say what we know.
Wait a sec. Go back to the torus. These are probably pinhead questions. One thing that's bothering me is, where did you get these? Where did you get the x and y in the first place?
Okay, so we said before.
They magically appeared.
Okay, so we said before that there is a linear space. Okay? Now, in fact, there were a set of equations were looking like this. So I could actually write down all these equations in a matrix.
Okay.
And then I could actually say,
you just find it from myself.
Compute the null space. Now, the null space now gives me some set of harmonic guys. And any linear combination will be harmonic. So what I've talked about here now is I picked two of them essentially randomly. What I've said here is true for any two. Now, in the genus 1, there's only dimension is 2 anyway, so they're all very related. You can't pick, I mean, you can pick one that's very different from the other, but once you pick two, you've kind of picked them all anyway. But okay, I picked two randomly. As long as they're linearly independent, the argument goes. Okay, so I solved the null space. That's a matrix operation, and then I sort of picked.
So the other thing that was bothering me is, what was preventing the boundary from boundary simple?
Yeah, so this is a trick. That's the part I did gloss over that. And I'll tell you, when I say some fancy words that I don't understand, you'll see why I glossed over it. So there is no boundary, right? Because it's torus. This is a doubly periodic infinite covering, all right? But you still would wonder, well, maybe somehow it crosses over itself before doing this doubly periodic, right? And trust me, the other author is Dylan Thurston, so he's in the math department, so he can say fancy words and I believe him. It has to do with the fact that there's like only one universal cover of the universal cover of the torus, and blah 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 blah. So it actually is.
It can't happen. You're saying.
There's a subtle. It's a statement. We actually don't in the paper. We actually don't state it because Dylan wrote the proof and I didn't understand it, so I waved my hands. So yes, you do need one more step to argue the global, and that step requires. I mean, Dylan said, "Oh, it's obvious." Fundamental, universal covering of this and this. But you couldn't even define the proof without, without having read at least 20 pages, if not 200 pages of something the graphics people probably haven't seen. So it would be nice if there were sort of a self-contained proof that doesn't require any knowledge of homology, but, I don't know it. And again, I don't even remember. I'd have to sit down and think, and then I could probably remember the magic words that make this happen. But I don't know. You're right. I did skip that completely. Get a candy. Okay. All right, so genus G greater than 1. The short answer is it's going to be more complicated. So we're not going to be completely satisfied with what we get. We'll just tell you what we get. So 2 minus 2G is now negative. That means if I pick a harmonic one form and I look at it, I'm going to find some saddles because of the counting theorem, right? So that means when I do some drawing, there might be something bad that happens because there's saddles in the one form, so I can't always argue that everything in the drawing looks nice because perfectly nice drawings have no saddles, and we know there are going to be saddles. So we're already kind of worried, and correctly so. Okay, so I'm going to explain the idea. This is a restatement of what Gu and Yao do. The idea is to isolate the badness. Okay, so there could be badness in these one forms. I picked 2 of them, but maybe I want to not pick them both at random. Let's pick one guy, and let's pick the other one to somehow be compatible with the first one that I chose. Okay? And what I'm going to say in a second, what I mean exactly by compatible. Well, actually, I'll say it now. What I want to happen is, if there's a saddle at a vertex in this one form, I'm going to want there to be another saddle at that same vertex in the other one form. And I want it to be nicely set up so much so that when I integrate them, what I get is a nice double wheel. So this is a double wheel. It goes around. Okay, that's not a wheel. It's not as nice as we'd like, but it's not. I mean, it's well defined. Okay, so possibly if I pick my 2 one forms, the saddles will coincide in the x and the y's just so that I get a double wheel. This would be allowed too. This is a doubly convex face. All my turns are sort of convex, but I have to go around twice before I match up. Okay, maybe I pick my one form so that the face is a saddle in face 87, and the other one form also has a saddle in face 87. And moreover, they're perfectly just balanced so that when I do a drawing, this comes out. All right? And if that happens, we're going to say that my 2 one forms are compatible. What can I do? So first, let's see how can we do this. So here's an algorithm. I'm not saying this.
Just a set.
Yeah.
Are you going to later tell me why it's okay to just have this isolated bad?
Yes, I'll tell you why I want to do. I'm not going to tell you why it's okay, but I'm going to tell you why it makes things not less than horrible.
Okay.
Okay. I'll tell you. We'll have full disclosure in a second. Yes. Okay. So first, let's see if we can do this. So here's an algorithm. Step 1 is pick a first random harmonic one form. Step 2 is look for a mate. Now, I just look for a mate. This idea means that it actually can be set up as a linear program, okay? Because it really has to do with orientations, and it's an inequality, linear inequality. Once you've picked one, it's a bilinear inequality with two forms. Once you've picked one, it's linear. So you can actually set up a linear program that states that all of my saddles, when I draw them, when I pick the mate, I get a double wheel or a double thing. Now, the linear program may be infeasible. You can pick a harmonic one form for which there is no compatible mate, in which case you throw away that first harmonic one form and pick again. Okay? So, again, I'm going to pick one randomly. I'm going to use linear programming. That's going to require the second one to be picked compatibly. This may or may not succeed.
I don't remember this in Guanyao.
It's not in Guanyao. What this proves is that Guanyao don't do linear programming. They have a specific matrix that says if you give me one, I multiply it by this matrix to give me the other. Okay? And the fact that the linear programming can't find a solution implies that that solution, which is simpler, can't work. So their idea is to try to isolate these things. That's the motivation. But their algorithm in fact can't always work. Okay? So they don't. This is not from Guanyao. This is from Work-Gosselin version. Okay. But if we find a linear programming solution, if it's feasible, then all the saddles will be compatible. Okay? So this is an if statement. So now I get to John's question. What's good about this? And it's only so good. It's not so great. It's not amazingly good. Here's the theorem. It's kind of another checking theorem. If all the saddles are compatible, then all the other faces will be convex, and all of the vertices are wheels. Okay, so we basically, it's this idea, we've isolated the badness in a couple guys, and that's going to argue then that everywhere else will be locally good. Okay, that's why we're doing this. So in this case here was our two-hole torus. So lots of neighborhoods here look quite nice here locally. Here's a vertex, and you blow it up. That's actually a double wheel there. Okay, and because there's a double wheel here, other stuff can actually overlap. Right? This arm here could overlap with this arm here because, once something goes wrong somewhere, all bets are off. There could be overlapping stuff, but that still means that locally this thing, if I look at it alone, it's fine, and if I look at this alone, it's fine. Okay? So so what we get here is that for higher genus, I can look for compatibility. I might be successful. If I am successful, then locally I have embeddings, not necessarily global. And these local embeddings are all consistent. There's no real important point. There's no boundary. It doesn't make a difference where I start. Any region that I run, if I run another region that overlaps, they're going to agree up to translation. So there's no real arbitrary choices here, other than the fact that the method didn't quite work. Right? Which leaves us with the question: is this useful? Such an animal. And the short answer is going to be, I'm not sure yet. People have claimed it is and are trying to use it, and I think the jury is still out. One way you could look at it is you could do embeddings of submesh disks, and whenever they overlap, they're going to agree up to translation. Okay, so that's actually just a restatement of what I've got. Is that nice? Well, I don't know. Maybe it's nice. It can be, in theory, used for seamless conformal parameterization in some way, and so people have used these things for parameterization. The nice thing is, so the bad thing is there are these double things, and so you get overlaps. But that's the bad thing. The good thing is there's really no notion of boundary. So there is sort of a natural smoothness in this construction.
I thought they had singular points, not these overlap.
Double faces?
Yeah.
Okay. So another exercise. What kind of mesh would this never happen in? And with what kind of faces could this never happen?
Triangle mesh.
Triangles. Because this is a 6, right? There's no way to go around twice with only 3 straight lines. So if you deal with triangle meshes, These just can't ever happen sort of a priori. And so these did not appear in the triangle mesh case. But just for, so here I'm putting it here for sort of completeness. If the mesh wasn't triangular, if you had, you actually need, though, 5 edges, I think, 5 or more, in order to go around twice with straight lines.
So Shlomo, is there just a simple way of, given you have these few double-wheel vertices, to just cut based on those so that you then have a parameterization?
That's effectively what Gu and Yao do. Yes, effectively they cut, so that each one is a
Starting
disk.
with that guy.
They cut sort of from wheel to wheel. Yes, that's effectively the way it's used.
They always come in pairs?
There's always 2 minus, if they all have they're all single multiplicity saddles, it's 2g minus 2, so it is an even number. So there is some, so that yes, there's generally an evenness going on here. But yeah, this is kind of getting into like, this sort of the question of how do you use these, and I didn't want to get into it. Yes, you could try to cut between them, and that's actually where, some of the subtlety perhaps lies in interpreting, what this is. In terms of just the pure questions of these forms, I'll leave you with a couple open questions. Which vertices can this vertex? Is there? I picked some. Can it be a saddle? Not all vertices can be saddles. Some can be saddles, but for which there cannot actually be a mate, so you get a double wheel. So which vertices can be saddles but can't be double wheels? Which oneforms can have compatible mates? All these things we don't know. We don't know answers to. I can give you some examples of ones. Typically, things with very low connectivity don't have enough freedom to like bend around in some sense, and so you have a region, and the whole region has like a triangle sort of locking it in. Then you can't get double stuff going on because there'd be so there's interesting sort of global connectivity issues that probably would answer some of these questions, which I don't know the answer to. Summary. Okay, so what have we done? We have talked about oneforms, which were sort of easy and useful, maybe. They gave us a proof of Tut's theorem. So now whenever you use Tut, which many of you use daily, you'll now at least sleep better at night that you know why it works. We talked about a somewhat slightly unsatisfying extension to non-convex boundaries, and an extension to higher genus, which was sort of completely nice for toruses, and again, sort of up in the air exactly what you can do with it for higher genus, but we sort of pushed that as far as we can understand those in terms of what you can and can't get from them. And that is the end.
It seems very much more like pure math than engineering to me.
Oh no.
Yeah, well, let's see.
Is that an insult?
No, it's not an insult. It's not, but it just...
Is that a praise?
That's what it is. It is what it is.
Especially the questions you asked at the end. It's like, do engineers care about those questions? I doubt it, but I could see that mathematicians would care a lot about those. They're interesting.
Well, you care about it if you're modeling something and it has 2 holes in it. And
well, but we have ways of dealing with these things already without all this machinery.
Yeah. So now we're getting into editorial, perhaps. Yeah, it is definitely not. It's got more lemmas than anything I've ever written before. Why? Well, because we're friendly with guys in math. I don't know why, but yeah, it definitely is. It's aiming more on the theoretical and less on the. But I think those questions are some of those open questions would be certainly the open question of a non-convex boundary is very very practical. I think just understanding those. I think once you know the answer to those questions of what can and can't happen, I think once you know the answer, you could maybe be in a better position to decide whether or not it was useful or not. It could be that the answer is useful, tells you something useful, or the answer turns out to be not very So we can talk more about the editorial offline. Anything else?
Parameterization schemes solve for vertex coordinates. So this suggests that one could instead solve directly for the one form, their equivalent, I guess, right?
Yeah, that's effectively what's happening. You're solving for, well, in this case, they're solving specifically using harmonic and picking random ones. But yes, sort of the first order bit here is that the elements that one is arguing about are differences, and not values. And because you get these differences that have nice consistent properties, then everything sort of, you can just add them up and get things. And so any pair of closed one-forms would allow you to make a drawing. With at least it would be path invariant. So it wouldn't have to be, the harmonic is a sort of a specific linear system, et cetera, et cetera. But one could imagine other constructions that are not exactly this construction, but are still based on using differences as.
The benefit of differences is you can have periodic structures like the genus 1 structure.
Yeah, I mean, I think that's probably a good way of sort of summarizing what's working, what's going on here. That you're solving with differences, and therefore you don't have to worry about totals and boundaries, et cetera. You deal with those at the end. You solve everything with differences, and then you figure out if you can make any sense out of it by putting some point. I think there were some tech reports I saw, people who did things like, instead of solving for differences, solve for like angles or lengths or other sort of difference type properties, and use that as the primary unknowns, and then solve for those, and then again had some kind of integration process to turn that into a drawing. So this idea does generalize, conceptually push that further. Okay, thank you very much.